All right. Y'all ready for some C this morning? Excellent. I don't think we have any announcements or anything pertinent to that to deal with today, so we might as well just get right into it because we've got a lot to cover and not a lot of time to cover it in. So, last time we talked about the manner in which C programs are compiled, and we talked about C programs. We saw some C syntax. We did some basic comparisons of overall C structure to Python. We learned that C is much less strict about things that you might expect it to be strict about, like what line each thing is on, having lines of code spanning as many lines in the file as you may wish, so long as you have enough tokens. So, any questions about anything before we get into it? Okay. So, one of the obvious differences that you'll notice between C and Python is that C has a main function. Python does not seemingly have a main function. As I explained last time, the actual sad truth of it is that Python does in fact have a main function. That main function is just implicitly the whole Python script, rather than being sectioned off in one section of the source code file. However, in C, as opposed to Python, execution begins on the first line of the main function and terminates when execution reaches a return statement inside of main, or when the program reaches the end of the main function without having returned anything. When you reach the end of a function in C without having explicitly returned anything, the compiler will insert return 0, which is a good thing to know. So, a main function is required for compilation. This is a question that we had last time in class. You can write a C source code file that does not contain a main function. This is the typical way that you would write a library file or a file to be imported by your C program, right? You can fill a file with just functions and exclude main, but the idea is that it would be at some point imported by a C file with a main function so that those functions might actually be called. It's like the difference between declaring a function and actually using it. Furthermore, trying to put regular statements into the global namespace, or to put assignment statements or if statements or things of that nature outside of any function constitutes a syntax error. You can declare global variables in this manner, but of course, as any good programming teacher will tell you, the use of global variables is strongly discouraged in most situations. Does anybody have any idea why? Okay, maybe I should back up. How many people know the difference between a local and a global variable? Good, so they did teach you something. So, can anybody hazard a guess why we discourage the use of global variables? Yes?
Because you might change the value of that global variable in some function, and then you might not remember that, and it makes it very difficult to debug.
Yes. So your functions may be modifying global variables in manners which you do not expect. Basically, the more common state which is held by a program, the more different strange error states you can be in. There's actually a good programming principle in general is to minimize the amount of state that you hold, period. It's, the less state there is, the fewer different states you can have which cause errors. This is sort of the design principle behind certain other programming paradigms, such as the functional paradigm. You have, I think, you might be tired of me talking about a programming language that you guys have probably never heard of before this classroom, but in the Haskell programming language, you don't even have state, not directly. You also don't have loops. Everything is done with recursion. But it's a good principle to try to minimize the amount of state that you're using at any given time. Everything, as far as that's possible, should be done with explicit inputs and outputs, right? So what this does, right, the design principle that we're working towards is the principle of modularization, right? You want to think of your programs as being like Legos. They have very specific interfaces with other Lego pieces. You pop the bricks together to make more interesting shapes, but the bricks themselves are simple, right? This is the idea that this is what we want to have happen anytime we write a program. So use of global variables counteracts good design principle in that it counteracts the principle of modularization. The whole idea behind modularization is that you can take a segment of a program, right? Take some sub-algorithm, right? You have some sub-algorithm. You can draw a box around it, say explicitly what goes in, say explicitly what goes out, and nothing else goes in or out, right? That's what it means to modularize software. If you've been able to do this with like all of the pieces of all of the algorithms in your code, you sort of end up with something that looks like, you know, substituting circles, squares for circles, because they're faster to draw. You have inputs coming out, they feed into the inputs of other things, right? You want your software to kind of look something like this at the end, right? A series of modules, all with explicitly defined inputs and outputs, all performing one function or one set of simple functions. And that way, they all click together like Lego pieces. The thing is, every single global variable that you use is an implicit input and output to each one of the modules in here, right? So you kind of, global variables sort of constitute threads running through the entire execution, right? And you can see, even just now, how messy that makes this diagram, even for just one, right? We want clean programs. So, good. We'll talk about C functions, of course, in excruciating depth in the following weeks. But for now, it's sufficient to know that C functions operate more or less exactly the way that Python functions do, minus some of the more advanced features Python offers, such as default arguments. There's no such thing in C. Does that make sense? So good, so far so good? Excellent. So, I've already answered these a few times in terms of questions, but we'll just go over it one more time. The int keyword indicates main returns an integer value, and I know you guys are not used to the idea of declared data types, but you will be by the end of this class. A return value of 0 indicates that the program exited normally, i.e. with 0 errors. Any other return value typically indicates the program exited abnormally, that is to say, errors happen. In the old days, before error codes, the computers themselves gave you information about why programs fail. So back in the 70s, you would have manuals for programs like GCC, and you would have to flip through an index of error codes at the back when you got a non-zero exit status, and that would hopefully give you some information about why the program failed. So this is kind of like this is the legacy that that this design paradigm has come from. You'll see that there is a lot of legacy stuff built into C, given that it's a 50-year-old language. So, giving void as an argument indicates that this program is ignoring any past arguments. The void keyword may be omitted. Very briefly, if you do not put a void here, what this C program is doing is acquiring command line arguments. We'll have some slides to show how to do that later on in the course. We need to sort of know how to work with strings and character arrays first. But basically, you can pass information in during the program invocation in the same way that we pass file names and flags into the GCC invocation, which performs compilation. It's the same mechanism. Make sense? Question?
When returning an abnormal value, does the value itself mean anything?
It can. It depends on the program. Basically, it depends on the program is the answer to that question. The program will be written in such a way that different error codes will mean different things for that program, right? You know, a -14 might mean something different from a -7, but all of that will be like specific status indicators about the program that produced the error. Does that make sense? We are not talking about system errors here, like dividing by 0 or running into a seg fault. Does that make sense? So the difference here, this is an error that is produced by the program that does not result from the program crashing. Important distinction. So, printing strings should be nothing new, but let's go over it anyways. So printf, print function, is the equivalent of Python's print function without the f. The biggest difference is that printf does not automatically append the new line character to the end of the string. You guys even know what the new line character is? How many people have no idea what I'm talking about? Okay, good. So, in this example, from one string to the next new line character, everyone loves Lisp. These 3 print statements will produce only 2 lines when printed because there's only one new line character here. And in fact, because there's been a new line omitted at the end of this, the bash prompt will actually show up on this same line here in terminal. So, in general, you may be thinking to yourself, why might this be useful? It gives you the ability to run a loop, for example, and count out a number of numbers all along the same line and then terminate them all with a new line character. And other similarly fancy printing methods. But, and it's not like you can't do this in Python. In Python, the print function has a hidden argument end where you can specify what the end character of a print operation is. It defaults to new line, but you can set it to a null character and thereby perform the same thing in Python as well as in C. However, this is what it's like in C, and there's no option to set an automatic end character for this string. You just have to put it in manually. Does that make sense? Cool. So, string formatting. I've already said this, but I'll say it again. String formatting should also be nothing new, but there are some important differences. So in Python, strings which are delimited by double quotes are exactly equivalent to strings which are delimited by single quotes. There is no semantic difference between these two. This is not the case in C. In C, double quotes are string delimiters, single quotes are single character delimiters. It's actually not, it's like many tick marks, many characters, single tick marks, single character. It's mnemonic, but that might throw you off if you, you know, it won't throw you off for long because as soon as you stick that in the compiler, it's going to complain at you that you have like a character that's many characters long and that's incorrect, which is correct. So, you know, you should, like a lot of the stuff we're talking about in this, it's like in this lecture, run it through the compiler once and you should be able to figure it out from the error messages, but you know, nevertheless. One of the reasons that, you know, you're a poor, humble professor who hates Python for mysterious reasons. One of the reasons I hate Python is because it pretends not to have characters. In Python, if you try to create a string, if you try to create a single character data point, it will automatically make it a string, right? Like characters are singleton strings in Python. And that's silly because characters are just character codes. There's no data structure associated with a single character, right? All it really is, like once you get into the compiler, what it does is it substitutes the character that you've specified for its ASCII value, and then it uses it and computes it just like it was any other number. So, you know, but Python goes to a lot of trouble to try to fool you into thinking that there's no such thing as a single character, when that's obviously not the case. But anyway, so we have a number of special characters. In order to access special characters, which are often ones that do not have a button on the keyboard, things like, well, I guess new line would be enter and tab would be tab, but you know, just use /t instead of the actual tab character, please. In order to access the extended set of characters, you must put a backslash before the character indicating the character you want in the string. One of the two of the ones that are sort of interesting now that weren't interesting previously are backslash itself. So to get a backslash in your string, you hit backslash twice, right? So you're escaping but the backslash itself, and the quote, the double quote. So previously, one of the Python workarounds for inserting single or double quotes into a string was to use the opposite character as a delimiter, right? You can use double quotes in strings delimited by single quotes. However, since everything's done in double quotes, what happens if you want to put double quotes into something delimited by double quotes? You escape them, right? Make sense? There's one that's going to be a lot more important as we get sort of down into the weeds with this course, and that's going to be the null character, which is \0. The null character is used implicitly to terminate all strings in C. Okay. Perhaps I should leave this for later, but here's a preview of coming attractions. So, arrays, right? In C, you don't have lists, you don't have tuples, you don't have sets, you don't have dictionaries, and you don't even have strings in the Python sense. You got one data structure, and that's the array. Anything more complicated than that, you either have to import a library or build it yourself. Arrays are not aware of how long they are. There's no way to access the size of an array, especially once it's been passed into another function. Like you can, if it's a static array declared in the same function that you're trying to find the size of it, but if you're passing that to another function, once it's inside that new function, basically there's no equivalent of the len length function in Python. Arrays are not aware of how big they are. So, what's done with strings is that all strings are terminated by the null character. The null character indicates the end of the string, so that operations on strings know when they are finished because they hit a null character and then it's done, right? So null characters don't actually print, but when you're allocating space for a string, if you don't allocate space for the null character, then your string won't have a null character, and then your operation over that string will continue on into unallocated garbage data after that array, and you might eventually hit a seg fault if you don't hit like a straight 0 first, because the ASCII value of a null character is 0. So that's, don't worry, we'll get there eventually, but I just wanted to give you a preview of that because you need to start thinking differently about data structures as well. Any questions? Yes.
It's a little bit like off topic, but if you wanted like 2 slashes, would you use 4? So you just put 3.
No, you'd have to do 4. If you wanted to do slash, like backslash, backslash. Yeah, each, the escape character is non-distributive. So here's an example where we are actually outputting and inputting some data from a program. Oh, stupid. Yeah. So, the following program collects 2 integers from the user and then outputs the sum of the 2 integers which have been input. All right? So I'll talk about printf first, and then we'll talk about the input scanf. So you'll notice that this right here seems to be doing the work of actually outputting the data. This is what's called a format tag. When you have a % sign existing inside of a string, followed by a series of characters, special characters, in this case just the D character, that indicates I am leaving a space in this string for whatever is being input into the string. That's then being passed to standard output and printed to the screen. So in this case, the second argument of the printf function, basically all arguments past the first one, which contains the string, are placed into whatever format tags have been left in the string in the order they appear, right? So if we had 2 in here, we'd have to have expression1, comma, expression2, and it would be put in order. Does that make sense? D means integer. I don't know why. I've never been able to figure it out, but D means integer. We're going to have a whole bunch of slides on the advanced features of format tags, but not until a little bit later in the course. So now let's talk about scanf. So scanf, the scan function, acquires inputs, or it acquires characters which have been placed into standard input, right? So you perform keystrokes on your keyboard. Those keystrokes are logged in standard input. The scanf function will collect up however many of those, it'll collect up to the point of the first new line character or enter or return key press, and it will attempt to format those characters according to the format tag provided. So in this case, what are we trying to read? I can't hear you. Thank you. If you want to read a straight string, it's S. So we've got some funny business going on right here, and we're kind of already getting to the point in the course where we have to talk about pointers a little bit. So we've declared two integers, I1 and I2, right? You're smiling too much for pointers being mentioned, man. So the scanf function does not simply drop the data into here in the manner of an assignment statement. This is how you might expect things to happen in other languages. Scanf expects the memory address that you want the data put into. So these guys are not in and of themselves memory addresses. To access the memory address of any variable, you use the ampersand prefix operator. So you slap an ampersand on the front, that elevates it from wanting to access the data contained by the variable to wanting to access the location at which that variable is being stored. That is the requirement of the scanf function. If you leave out the ampersand, it won't work. If you leave out the ampersand, actually, because it's expecting a memory address and you're providing it just a number, it will think that that just a number is a memory address, and it's unlikely to be inside of your valid memory. So that's likely to result in a seg fault. Right? It'll probably give you a warning in the compiler, though, that you're passing a pointer of an incompatible type or something like that. Make sense? Question?
Why do you have the lowercase I before the integer 1?
Why do I have the lowercase I before the integer 1?
That's the name of the integer?
This guy?
Yeah.
Yes. Variables can't start with numbers. Variable identifiers can't start with numbers. So yeah, I just declared two variables, I1 and I2. It would have been equivalent if I had said X and Y, or beef and jerky. You know, it doesn't, foo and bar. It's just variable names.
So what is their value?
They are not initialized. That's actually a good point. I'm glad you brought that up. Thank you. So, because this might be our first instance of uninitialized variables. So, you may notice that no value is being assigned to these variables. It is not actually required in C that your variables be assigned to upon declaration. Many sort of modern programming languages will use whatever value you put in here, like Python, to type these variables, right? It's like, oh, well, you're assigning a Boolean to it, so I guess you want a Boolean variable here, you know? And, you know, it's like, oh, you just gave me the value 3. 3 could be an integer or a float, so I'm going to assume it's both until it resolves itself further down the line, which is a process known as parametric polymorphism. But in C, you don't actually have to initialize these bad boys, right? So the question is, if they're uninitialized, what do they contain? Because it's memory, right? And memory always has to have some definite value. It's all ones and zeros at the base. Idea?
I would assume that once if you have an uninitialized variable, it would be whatever was in memory that was not there beforehand.
Exactly. These two variables will contain whatever is held in memory by the previous state of the operating system or previous programs that have been run. And you might say, hey, isn't that a security problem? And it's like, well, no, actually, because you're looking at what, like 64 bits out of how many bits on your RAM card? You know? Data is only useful when it's in context. Because the data is no longer in context, we have no idea what that very small segment of memory might mean. So, it's just garbage. I will refer to it several times in class as smelly garbage data. Incidentally, arrays which are declared and not populated with values are filled with the same. So, Yeah, so they are essentially data is being put into them during the scanf operation. Prior to that, they contain nothing of interest, although they do contain something. You could read them if you wanted to. Does that make sense? Good. Any other questions? So far, very good questions. Excellent. Yes?
So, in this would require the user typing in data of some sort, right? So
Yes.
So the second, like after your second integer, since there's no line break on the scanf function, would it start on the same line that you put in integers? Or does that automatically do that?
Scanf itself is automatically looking for the new line character, so we don't have to put it in the format string.
So like at the end of scanf, it'll automatically take a new line for whatever's next?
It's more like it will detect that a new line has been produced. So let's just run this example and we'll see how it operates. So, simple dots. So this is a live coding segment. The appropriate thing to do during live coding segments is to type along with prof. So, what did I do? F11? There we go. All right. So, include stdio.h int main. I'm going to leave out the void. I'm going to avoid the void KO int I1 int I2 printf. Enter your first integer. And I'm going to do it a little more fancy than it is here. I'm going to put a couple of characters at the end there. It's good whenever you're expecting the user to provide you information that you give them something that looks like a command prompt. Scanf. Address of I1. Printf. Well, the programmer's secret weapon is copy paste, not from other people's work. Copying, pasting your own is fine. In fact, it's encouraged. All of good programmers know the value of find and replace. There we go. Printf. The sum of these is D I1 plus I2. And save that. So, going to compile this, gcc simple.c, out simple. There we go. No compiler errors or warnings. In fact, let's check all warnings. Nope. So, just as an interesting little aside, if I create an integer, or if I create a variable and then I don't use it, that actually shows up as a warning, which is kind of interesting. But I believe that doesn't show up. Yeah. So this is an example of one of the extended warnings provided by wall. If you don't invoke wall, it doesn't show you that you've got integers declared that you don't use. Because it doesn't really affect functionality, right? It's an efficiency thing. To use one more integer than you actually need is not the end of the world typically. But anyway. So you'll notice that I have, in addition to my C source code file, a green-colored executable file. In Linux, green typically means this file is executable. So, execute simple.c, or simple. Enter your first integer. 2. Enter your second integer. 2. The sum of these is 4. Simple, right? If I1 plus I2 is equal to is equal to 4, you don't have to follow this one. This is a joke. I'm telling a joke in the argument. Right? That's true. See? It's useful. But notice how that wasn't an error. It still compiled that. Right? So, in this case, if we enter 4 and 4, we get 8. But if we enter 2 and 2, we get 5. Right? That's a 1984 joke. Good. Good. And yes, so I also have the output in the slides. Any questions about that? 2 questions. Start with you, sir.
It's a bit confused. Why is it that Scana is like memory address? Why isn't it like
That's just simply the way these functions were coded. You just have to memorize it, what these functions expect. Again, other languages have critiqued this approach by doing things differently themselves. But yeah, I think it's because like the direct return value of the scanf function is something like the number of characters correctly interpreted or something like that. So like if you compare Python's input function, the return result of the input function is that which is read, right? In this case, it's probably something else like how many characters were read or something like that. So it's passing the actual output of scanf implicitly by using pointers. You had a question? You're gonna have to shout.
Why did you write this about C code?
Why did I add what?
Where did you write it?
Where did I write it? Oh, just in a folder in my operating system.
Is it the text file?
Yes, it's well, all C source code files are plain text files. Yes. Yeah.
You ran it?
I ran it by executing I compiled it first by executing GCC on my computer. However, my computer is Linux, so in Windows, if you're using Windows, you'll have to use some other, method that's a little more complicated, but ultimately should accomplish the same thing. Yeah. If you are at a loss as to how to install the correct software, you do have access to the PuTTY, if you download the PuTTY client, you can log into the Pascal server, which will provide you the precise same interface that I've been presenting here. However, I would recommend using the Nano editor rather than using Get like I'm using. So nano simple.c, and then it's just an editor that's right there in the terminal for you, so you don't have to hook up anything else. Make sense?
Yeah.
You, sir, you're gonna have to check.
What is the quotation marks around the percent code? Why?
Well, the percent. Okay. Well, best way to answer that is to just exclude them and see what happens. There. Because otherwise it's not a string, and it's expecting a string. Also, the percent sign character doesn't really mean anything. Expected expression before percent sign token is the error that you get. Make sense? Yeah. So this might be another point that's slightly uncomfortable for the perennial Python user. When a function expects something of a particular type, it means it. You can't pass things into functions that are of the wrong type. Period. Or not for any reason, not even once. Any other questions? Yes?
How do you know what type each function is expected?
You look it up.
Okay.
You look it up or you memorize it. Yeah. It's in the documentation. Any other questions? Hopefully you look it up and you memorize it after you look it up. Yes?
When working on assignments, if there's a function that's operating a different way than we were expecting it to, and we look on online and see maybe Stack Overflow just explaining how the function works, that wouldn't be considered plagiarism, right?
Reading reference is not plagiarism. Copying code is plagiarism. Also, the Piazza forums are there for your use. Yeah. Okay. Moving right along. A lot of you just failed to get that to compile, didn't you? Yeah. Well, that's a problem you're going to have to solve for yourself in short order in this class. So, you may have noticed that the preceding program uses variables. Variables in C work the same as variables in other C-based languages, such as Python. So, roughly speaking, you shouldn't, you already know how variables work, right? It's just a matter of there being a few little pieces that you may not be familiar with, right? So, in contrast to Python, C variables require explicit declaration. When you precede the variable name with a data type, that is its declaration. After that point, you do not need to provide the data type. It has been set. We haven't seen an example long enough to require that yet, but that's the case. A variable must be declared with a data type, in this case integer, like so. You can declare multiple variables on one line. You can declare floats, etc., etc. Variables may also be declared with an initial value, so as so. This is known as instantiation. So the difference is, in Python, variables are declared by their instantiation. In C and other C-based languages, variable instantiation and declaration are separate operations that optionally can occur at the same time. Does that make sense? Question?
If you assign, let's say, x equals 7.0, and you assign a full value, would that result from here?
Yes. Or truncation. It might be truncation, actually. We would have to check. But generally speaking, C is okay with you trying to assign the wrong type literal to something. Like, for example, if you have a declared character and you assign an ASCII code to it as an integer, it's not that it will convert, it's not that it performs conversion because there's nothing to convert because it's all integers at the base level, right? But it'll take your literal and it'll squeeze it into the space provided by a character, right? So basically, if you peel back its skin, C only really has two reasonably distinct data types. Floats are something else because they're something else, very much something else mathematically. But pretty much everything else, integers, booleans, characters, they're all integers of varying sizes, right? So a character is 8 or 16 bits. An integer is 32 bits. If you assign a 32-bit integer to a 16-bit slot, it will just chop the top off and leave the rest. And that's how it works. Anyway. Identifier naming conventions. Identifiers, and this includes both variable names and function names, and struct names, but we aren't there yet. Identifiers are legal if they contain only letters, digits, and underscores, and do not start with a digit. It's conventional to start variables with lowercase characters, so it's conventional that types be uppercase and variables and function names be lowercase for the first character. Identifiers are case sensitive, obviously. Here are some good practices. Starting identifiers with underscores may cause conflicts with identifiers generated by the compiler or with the standard library. Basically, don't use an underscore as the first character. You might run into a conflict. You should always use meaningful variable and function names, unlike the variables that I've been using so far in this class. They should always relate to what the purpose of the variable is or the purpose of the function. They should be descriptive. By convention, variables and functions begin with lowercase letters. Multi-word variable names can be separated by underscores or written in camel case. The standard library function scanf reads characters from the standard input buffer standard input. As so. The first argument is the format control string, which indicates the data type that should be input by the user. Other places you might use the type name itself. This format control string actually has a very large number of options that you can use to read things more efficiently or in the manner that you want. We'll, again, get into it a bit later on. It's a little rude. Our class isn't done yet. Anyway, so the second argument is the variable that we want scanf to put the data in, prepended with the address of operator ampersand. We will be covering it in depth when we talk about pointers. So, to print the value of a variable, you must use a format specifying placeholder in the first argument. Supply the variable as the second argument. Again, if you wish to put multiple of these in, you provide multiple comma delimited arguments past the string that you're printing. Question?
Could you just print out brackets and then just a variable name and nothing else?
No, that doesn't work because if you were to just printf I1 plus I2, I1 plus I2, the return type is an integer, not a string. The first argument is expecting a string. In fact, it's even worse than that because a string can be, or an integer can be interpreted as a character, but it has no null terminating character. So, not a good idea. It'll give you a type incompatibility error. Yes?
If you wanted to put in multiple integers, does it matter where the brackets are for the following argument?
I mean, they should be, like yes and no. So let's just do this quickly, right? And the product is D. There we go. This is the correct format. Oh. Can I not recompile it? Oh, scan. Oh, I left that in. Make sense? Good. All right. See ya.